All right, so now we can solve the system of equations. This is going to be some nonlinear system, so we're going to have to start with some initial guess for the nodal values of the field theta for the heat transfer problem. And this is our guess for the nodal values except for the nodes with essential boundary conditions, because for those nodes we actually know the value of theta. So if you go back to your residual, and then let's say that we order them, this is when it is helpful to have the nodes numbered such that the first nodes that are the ones with essential boundary conditions. So here, this global residual is size number of nodes. And like I said, the residual has to be zero, but not all of the residual is going to be zero, only for the nodes that don't have essential boundary conditions. So in this case, the first four nodes have essential boundary conditions. So actually, I only need R star to be zero, where R star is the residual corresponding to the nodes 5, 6, 7, 8. This is the actual system that I need to solve. The first part of the residual is not going to be zero, so I just need to ignore it. So that would be, this is my system of equations that I need to solve. Obviously for the initial guess, if I evaluate R star at that guess, right, of the nodal values, that is not going to be zero, right? Because my initial guess is probably not correct, so that's not going to be zero. So I need to do a Newton iteration. So for the Newton iteration, I need a K star. So I will evaluate K at that theta 0, right? And that's going to be this 8 by 8 matrix. But out of that 8 by 8 matrix, I will only take the part that corresponds to my nodes that don't have essential boundary conditions. So I'm going to take a subset out of that, which is my K star, which is in this case 4 by 4, right? So K star is the tangent. So rows and columns for nodes that don't have essential boundary conditions. Again, here, if you do it in such a way that the first nodes are the ones with essential boundary conditions, so notice that, so this will be like nodes with EBC, then it's just like a block, right? So then I don't need to worry about any of this. So all of that I can ignore. This is not always the case, as I'm gonna show in the second option. But in the first option, if you do it in such a way that you put all the nodes with essential boundary conditions first, then you can just basically take this subset of matrices. And then with that K star, then you'll get this increment of theta. So you will do increment of theta equals the iteration. So the first guess minus K star inverse times residual star, both of those evaluated at the initial guess, right? So this K star evaluated for that particular guess, and R star evaluated for that particular guess as well. And then just continue doing that, right? So then this just loop until convergence. So that's one way in which we're gonna solve the system. Then let me do a what if scenario. So what if the nodes with essential boundary conditions don't appear first? Well, in that case, you would need to get rid of the corresponding rows of R. So let's say that for some reason we have R equals, and that instead of being 1, 2, 3, 4, imagine that it's I know the nodes differently. So let me just maybe redo the mesh. So what if I have, it's the same mesh as before, But let's say that now I number the nodes 1, 2, 3, 4, 5, 6, 7, 8. Right, so in that case, the nodes with the essential boundary conditions are going to be 1, 4, 6, and 8. So now they are no longer, so 2, 3, 4, 5, 6, 7, 8. Not something like this. Because the nodes with the essential boundary condition are still these ones. So let's say that that happened, for example. Then I would need to create my R star should have basically only these two, this, and this. So that's how it should look like. So it should only have contributions from let me call it R1, R2, R3, R4, R5, R6, R7, R8. Should only have R2, R3, R5, and R7. Right? So even though I can assemble the entire thing, which is size number of nodes. I still need to isolate the subset of that only has the free nodes, or the degree of freedom nodes, right? And the same will be true for the K. So for the K, I will still have an 8x8 matrix, but now I need to get rid of the entire. So I have again 1, 2, 3, 4, 6, 8. 1, 2, 3, 4, 6, 8. So 2, 3, 2, 3. So again, I need to get rid of the rows and columns. So the entire row and column will be gone. The entire row and column will be gone. The entire row and column will be gone, and the entire row and column will be gone. And then I will make, that actually came out pretty. And then, so all of the things that are in between, those would form the end K star. How you do that? Well, I'm not going to explain on this video, but this is what you would have to do. You would have to assemble it in such a way that you end up with this. With this reduced K star, because that's what you need for the iterations. So that would be the example. In this case, in the Python notebook, I have the nodes number first. The nodes with essential boundary condition are number first. So actually, you can do the partitioning like I did here. But otherwise, you would have to do something like this. And then there's just one more option that I'm going to talk about in the